Hi everyone, welcome to this video lecture on paper 3 unit 1 aberrations. In this video lecture I would like to explain what is called aberration, what are the types of aberrations and their elimination methods. Aberration means the defects of images formed by lenses. Lenses are used in optical instruments like telescope, spectrometer, microscope, binocular, camera, spectacles, etc. The defects of images formed by lenses are called aberrations. Aberrations may be defined as the deviations from the actual size, shape and position of an image as calculated by the simple equations are called aberrations or defects produced by a lens. The aberrations are of two types: chromatic aberrations and monochromatic aberrations. Chromatic aberration. The aberrations produced in an image by the variation of refract index of the material with the wavelength or color of light are called chromatic aberrations. Monochromatic aberrations. The aberrations produced in image even when a monochromatic light is used are called monochromatic aberrations. Monochromatic aberrations are of five types: spherical aberration, coma, astigmatism, curvature of field and distortion. Here I would like to explain the chromatic aberration clearly. Chromatic aberration. The image of white object formed by a lens is colored and blurred. This defect of image is known as chromatic aberration. That means the lens is not able to form the image of white object as white image. The chromatic aberration is due to the fact that the refract index varies with color. We know that the focal length f of a lens is given by 1 by f is equal to mu minus 1 into 1 by r1 minus 1 by r2. This formula is called Lensmaker's formula. In this formula, mu is the refract index of the middle of the lens. R1 and R2 are the radii of curvatures. As the refract index mu for violet color is greater than that refract index mu for red color, and hence the focal length for red color is greater than the focal length for violet color, that is FR greater than FV in case of convex lens. Thus, when a parallel beam of white light is refracted through a lens, violet rays meet first and the red rays meet at farthest from the lens. The rays of intermediate colors meet in between FR and FV. If a screen is placed at FV, then the center of the image would be violet while the outer surface will be red. Similarly, if the screen is placed at FR, the center of the image will be red while the outer surface would be violet. For all other positions between FV and FR, the image is blurred. Thus, the image of white object formed by a lens is colored and blurred. This defect is called chromatic aberration. The chromatic aberration in case of convex lenses and concave lens are shown in figure. In this figure, the diagram here shows concave lens, convex lens. When a parallel beam of white rays incident on convex lens, after refraction, the light rays are split up into 7 colors: violet to red. Violet rays meet first and red rays meet farthest. In between FV and FR, the intermediate rays meet. In case of concave lens, the images are found on the left side of the lens. The chromatic aberration is of two types: longitudinal chromatic aberration and lateral chromatic aberration. Longitudinal chromatic aberration, the formation of images of different colors in different positions along the axis is known as longitudinal chromatic aberration or axial chromatic aberration. The distance between violet color image IV and red color image IR along the axis is a measure of the longitudinal chromatic aberration. Therefore, longitudinal chromatic aberration is equal to IR minus IV. Lateral chromatic aberration. The formation of image of different colors of different sizes perpendicular to axis is known as lateral chromatic aberration. This is due to the fact that magnification of white object is different for different colors. Lateral chromatic aberration is equal to BRAR minus BVAV, where BRAR is the height of red color image, BVAV is the height of violet color image. Now, I would like to explain the derivation of the expression for longitudinal chromatic aberration. Case 1. When the object is situated in infinity, we know that the focal length of lens is given by 1 by f is equal to mu minus 1 into 1 by r minus 1 by r2. If fv, fr and fi be the focal lengths of the lens for violet, red and yellow colors respectively, and mu v, mu r and mu y be the refractive indices respectively, then 1 by f is equal to mu v minus 1 into 1 by r minus 1 by r2, 1 by fr is equal to mu r minus 1 into 1 by r minus 1 by r2, and 1 by f is equal to mu y minus 1 into 1 by r minus 1 by r2. These three equations are written by 1, 2 and 3 respectively. Substituting the equation 2 from equation 1, we have 1 by fp minus 1 by fr is equal to mu v minus mu r into 1 by minus 1 by r2, or fr minus fv by fe into fr is equal to, on LCM we get fr minus fe by fr is equal to mu v minus mu r by u v minus 1 into mu v minus 1 into 1 by minus 1 by r2. That is fr minus fe by fi square is equal to mu v minus mu r by mu y minus 1 into 1 by fi. Here fe into fr is equal to fi square nearly. Fr minus fe by fi square is equal to omega by fi, where omega is equal to mu v minus mu r by mu minus 1 is called dispersive power of the metal of the lens. Therefore, fr minus fe is equal to omega into fi. That is the equation 4. This is the required expression for longitudinal chromatic aberration. Hence, the longitudinal chromatic aberration for a thin lens for an object at infinity is equal to the product of its mean focal length and dispersive power of its length. Now, case 2. When the object is situated at finite distance. For a thin lens, the relation between u, v and f is given by 1 by v minus 1 by u is equal to 1 by f. That is the equation 1. When the object is placed at a finite distance, u, the distance of image and focal lengths vary with color. Hence, differentiating equation 1, we get minus dv by b square is equal to minus df by f square, or dv by b square is equal to df by f square. That is equation 2. If the image distance and focal lengths for violet and red colors be Vv, Vr and Fe, Fr respectively, then dv is equal to Vr minus Vv and df is equal to Fr minus Fe is equal to omega into Fi, where Fi is the focal length for mean color, that is yellow color, and omega is the dispersive power of the metal of the lens. Substituting these values in equation 2, we get Vr minus Vv by Vy square is equal to omega into Fi by Fi square is equal to omega by Fi. Therefore, Vr minus Vv is equal to omega by Fi into V by square. That is equation 3. This equation gives the required expression for longitudinal chromatic aberration. This shows that the longitudinal chromatic aberration depends upon the dispersive power of the lens omega and the mean focal length Fi and the image distance for mean rays Vy. Now, I would like to explain the method of minimization of chromatic aberration. It is called achromatism. Achromatism of lenses. The minimization or removal of chromatic aberration is called achromatism. When two lenses are placed in such a way that the image formed by them is free from chromatic aberration, then the combination of lenses is called achromatic doublet and the phenomenon is known as achromatism. For achromatism, we have to use two types of combination of lenses. In the first combination, two thin lenses are placed in contact, and in the second combination, two thin lenses are separated by distance coaxially. Case 1. The condition for achromatism for two thin lenses in contact. An achromatic doublet is formed in such a way that all colors come to focus at one point. That is, all colors have the same focal length. That means the image of white object is white image. For a single lens, we have 1 by f is equal to mu minus 1 into 1 by r minus 1 by r2. This is called Lensmaker's formula. The change in focal length for corresponding change in refractive index can be obtained by differentiating equation 1. That is, d of 1 by f is equal to d mu into 1 by r minus 1 by r2. That is equation 2. Dividing equations 1 and 2, we get f into d of 1 by f is equal to d mu by mu minus 1. That is equal to omega, where omega is dispersive power of the material of the lens. Therefore, d of 1 by f is equal to omega by fy, omega by f. That is the equation 3. Let f1 and f2 be the focal lengths of the two lenses in contact, and omega 1 and omega 2 their dispersive powers between the two wavelengths for which the combination is to be achromatized. If capital F be the focal length of the combination, then 1 by capital F is equal to 1 by f1 plus 1 by f2. On differentiating, we get d of 1 by capital F is equal to d of 1 by f1 plus d of 1 by f2. From equation 3, we have d of 1 by f1 is equal to omega 1 by f1 and d of 1 by f2 is equal to omega 2 by f2. Therefore, d of 1 by capital F is equal to omega 1 by f1 plus omega 2 by f2. That is equation 4. For achromatic doublet, capital F and hence 1 by capital F should be constant. That means that should not change with color. That is, d of 1 by f is equal to 0. Therefore, omega 1 by f1 plus omega 2 by f2 is equal to 0. That is equation 5. Or f1 by f2 is equal to minus omega 1 by omega 2. This is the required condition. Thus, the focal length should be in direct ratio of the dispersive powers of the two lenses. As omega 1 and omega 2 are positive quantities, f1 and f2 must be with positive signs. That is, if one lens is convex, the other lenses should be concave. In actual practice, one is a biconvex lens of crown glass, while the other is a plano-convex lens of dense front glass. This combination is called achromatic doublet. In this way, we can minimize the chromatic aberration. Now, the second condition. The condition for achromatism for two lenses separated by distance coaxially. Let us consider two convex lenses of focal lengths f1 and f2 separated by a suitable distance x. If capital F is the combined focal length of the combination, then 1 by capital F is equal to 1 by f1 plus 1 by f2 minus x by f1 f2. That is equation 1. The change in 1 by capital F is given by d of 1 by capital F is equal to d of 1 by f1 plus d of 1 by f2 minus d of x by f1 f2. On expanding, we get d of 1 by f1 plus d of 1 by f2 minus x into 1 by f2 into d of 1 by f1 plus 1 by f1 into d of 1 by f1, d of 1 by f2. But we know that d of 1 by f1 is equal to omega 1 by f1 and d of 1 by f2 is equal to omega 2 by f2. Then d of 1 by capital F is equal to omega 1 by f1 plus omega 2 by f2 minus x by f2 into omega 1 by f1 minus x by f1 into omega 2 by f2. That is equation 3. For an achromatic combination, the focal length capital F or 1 by capital F should not change with color, that is d of 1 by capital F is equal to 0. Therefore 0 is equal to omega 1 by f1 plus omega 2 by f2 minus omega 2x minus omega 2x plus omega 1x by f1 f2, or x into omega 1 plus omega 2 by f1 f2 is equal to omega 1 f2 plus omega 2 f1 by f1 f2. Both sides f1 f2 should be cancelled. Therefore x is equal to omega 1 f2 plus omega 2 f1 by omega 1 plus omega 2. That is equation 4. When the two lenses are made of the same material, that is omega 1 is equal to omega 2 is equal to omega, then x is equal to omega f2 plus omega f1 by omega plus omega, that is equal to omega into f1 plus f2 by 2 omega. Therefore x is equal to f1 plus f2 by 2, that is equation 5. This is the required condition. That means the separation between the two lenses must be equal to the mean of focal lengths of the two lenses. In this way we can eliminate the chromatic aberration by using a lens combination called achromatic doublet. Now I will explain the defect spherical aberration and the minimization of spherical aberration in the next video lecture. Thank you.